Molecular compounds. We just finished talking about ionic compounds. What's the characteristic of a molecular compound? What's it composed of? Nonmetals. Ionic compounds contain a metal and a nonmetal, and molecular compounds have nonmetals. We have to have a different set of naming rules for molecular compounds because they don't form ions, and so we can't use charges to predict how they're going to combine. In fact, we can get multiple compounds from the same two elements. The example is nitrogen and oxygen. 1, 2, 3, 4, 5, 6 different compounds between nitrogen and oxygen. And you can't predict this just by looking at the periodic table. So we need a different set of rules to name these guys. Molecular compounds, again, are composed of nonmetals. And the ones we're going to look at will be 2 nonmetals. We use numerical prefixes to indicate how many atoms of each element are present. These are the prefixes over here. They're standard Greek prefixes: mono, di, tri, tetra, penta, hexa, etc. So we list the more metal-like element first. How do you decide that? Well, usually it's the element with the smallest group number, or if they're in the same group, then we write the element with the greatest row number first. If we look at the periodic table and say, look at row 3, we see aluminum and silicon and phosphorus and sulfur. Is aluminum a metal or a nonmetal? It's a metal. That wasn't a trick question. And next to it is silicon. Silicon is a semi-metal, and then one over to the right is phosphorus, which is a nonmetal. As you go across to the right on the periodic table, things become more nonmetal. As you go to the left, they become more metallic. So generally the element with the smallest group number, that'll be the one to the left. If we look up and down in a column, say group 4, we've got carbon at the top, that's a nonmetal, and then it goes semi-metal, semi-metal, metal. As we go down, so greatest row number is more metallic. We are going to learn how to name binary molecular compounds, 2 elements. So this is the pattern. A prefix is used before the name of the first element to tell how many atoms of that element. And then there's a space. It's not real visible there. And a prefix and the name of the second element, but we're going to change the ending of its name to "ide." Just like it was an anion, except it isn't. And then, of course, there have to be some exceptions. So if there's only one atom of the first element, then we omit the prefix mono, because chemists have a thing against the number 1, right? So we don't like the prefix mono either. We're only going to use it if we have to. So NO2. Well, this is nitrogen and oxygen. There's 1 nitrogen. We're going to leave off the mono because we don't like the number 1, and so we're going to call this nitrogen. And then there's 2 oxygens, so we use the prefix di, oxide. Nitrogen dioxide. There are 2 compounds that are special, H2O and NH3. They always use their common names. So these are the equivalents of Cher and the artist formerly known as Prince, or whatever he's called by now. But he was Prince, one name, right? H2O is always called water, and NH3 is always called ammonia. Even though they do have systematic names, we'd never use them. So let's do a couple of examples. What would be the name for this compound, N2O5? Dinitrogen pentaoxide. There's 2 nitrogens, so we put di in front of it and leave a space, and then pentaoxide. Changing the ending to "ide." There are some other subtleties, and I am not going to try to trick you about these on an exam or anything. Pentaoxide, here we have a prefix ending in a vowel and an element starting with a vowel. So sometimes what you'll see is the last letter, the vowel from the prefix gets dropped, and so some places you'll see it written pentoxide. And the International Union of Pure and Applied Chemistry does have an official set of rules, but not everybody remembers all the little details. And I figure, you know, if the chemistry textbooks can't agree about what they're going to call this, I'm not going to get hung up on it with you. But I want to point that out to you so that if you see pentoxide, don't think that that's necessarily wrong because the A is missing. Another example of where that happens is monooxide. Doesn't that just look dumb? Monoxide? What is that? We leave one of the O's off. Monoxide as in carbon monoxide. Okay, but I won't try to trick you on that. How about writing the formula for phosphorus tribromide? Well, how many phosphorus? 1, because we didn't say otherwise. So just a P. We didn't have the mono, and we don't write the 1. It's a pattern. Tribromide. 3 bromines. So Br3. PBr3. Any questions? Students usually get the naming of the molecular compounds, so I don't elaborate on it too much. The thing is, they like it too much, and they try to use it for everything else. 2 nonmetals is the only time you can use it. If you've got a metal in there, you can't use these prefixes. Another group of things to name, acids. Acids have a special naming system. So how do we recognize acids? Well, one definition of acids is that these are molecular compounds that release hydrogen ions when dissolved in water. That's the definition we're going to use for this. So what we see is that acids are composed of hydrogen, and usually that hydrogen is written first in the formula, and then there will be 1 or more nonmetals after that. So here we have HCl. So basically, if the compound formula starts with H, it's an acid. So that makes them fairly easy to recognize. So HCl, this is a molecular compound. It's 2 nonmetals, hydrogen and chlorine. But when it's dissolved in water, it ionizes and forms hydrogen ions and chloride ions. And this little AQ means aqueous, aqueous dissolved in water. So H plus with AQ after it means those are hydrogen ions dissolved in water, chloride ions dissolved in water. So if we see just HCl, we're going to name that as a molecular compound. If we see HCl dissolved in water, HCl aqueous, that's an acid. And we'll name it as an acid. How would we name HCl as a molecular compound? It's hydrogen chloride. Now you might ask, why isn't it hydrogen monochloride? Well, that's a good question. Again, that's one of those kind of weird exception things. If there's only 1 known compound between the 2 elements, then we leave off the second mono also. That's where things get a little messy. Somebody had a question? So if you have a compound that starts with hydrogen, it's not considered an acid unless it can dissolve in water. So if it's dissolved in water, we name it as an acid. If it's a gas or a solid or something all by itself, it's named as a molecular compound. So how do we name the acids? Oh, I guess we're going to talk about the acids first. Characteristics of acids. Acids have a sour taste. My kids like those candies, Sour Patch Kids. They're so sour. I don't like sour stuff. I like sweet stuff. They like sour stuff. Do you know what makes Sour Patch Kids so sour? Acid. There's acid on children's candy? guess. It's not the acid drug acid. It's citric acid and malic acid. It's fruit acids. But that's what makes it taste so sour. That's why lemons are sour, because they have acid in them. Other characteristics of acids, they dissolve many metals, not all of them, but zinc, iron, and magnesium will dissolve in acids. Gold, silver, and platinum do not, which is one of the reasons why people make jewelry out of gold, silver, and platinum. And formulas of these acids usually start with H, like HCl, H2SO4. So there's, of course, there has to be categories of acids too. We've got everything just broken into categories, right? 2 types, and each of them has a slightly different naming system. So we've got the binary acids and the oxyacids. I prefer to think of identifying the oxyacids, and then the other acids are going to be binary acids. The oxyacids start with hydrogen, like all acids do, and then they have an oxyanion in them, like nitrate or sulfate or something like that. Binary acids are composed of hydrogen and a nonmetal. Binary meaning 2. The issue I have with that description is that there is an acid, HCN, which is named using the binary acid rules, but it has 3 elements in it. 3 nonmetals, but it's 3 elements. So how do we call that a binary acid? So that's why I think of oxyacids and the other kind of acid. So I get hung up on details. You've probably noticed that. Okay, so let's look at the binary acids, the other acids. When we name these, we use the prefix hydro. And then the middle of the acid's name is based on the name of the nonmetal, and then we change the ending of that name to ic, and then we add the word acid on the end. So like most compounds, these are going to have 2 words in their name. Hydro something ic space acid. So HF. This is a big empty slide. Well, you always have to ask yourself, what kind of a compound is this? It starts with H. It's probably an acid. Look, it's dissolved in water. Oh yeah, it's an acid. We've got hydrogen and fluorine, no oxygen. So we're going to use the prefix hydro. And then from fluorine, we're going to take the fluor part and then ic. Instead of fluoride, it's fluoric, hydrofluoric acid. Any questions? The nice thing about the acid names is they all have the word acid in them, so it's very easy to recognize what they are from their names. The oxyacids. These are named based on the name of the oxyanion that is in them. So you have to identify what's the oxyanion. We need an example here. So let's say HNO3, aqueous. So we look at that. It starts with H. It's dissolved in water. It's an acid. Look, it's got oxygen in it. This is an oxyacid. So then what we're trying to do is figure out what is the name of that oxyanion. Take the hydrogen off or cover it up. What's left? You have to name it. So NO3 is nitrate. So nitrate. And these oxyacids are either going to end in ate or ite. So if the oxyanion ends in ate, well, this is probably a better place. If it ends in ate, then we change that ate ending to ic. So nitrate becomes nitric, and then we stick the word acid on there. If it ends in ite, we change it to us, and then we add the word acid. So this is one of many situations in chemistry where we have 2 pairs of things, and we have to remember how they correlate. I'm not good at just remembering random things. I need some trick or some clue. So, silly sentence. Rick ate him before he could bite us. Is that silly? I hope he is not a person. Maybe I don't know, some sort of an animal. Oh, I'm running out of space. That's not what I meant to do. Rick ate him before he could bite us. It's really not ideal to wrap it around the corner like that. So how does this help you remember? Ick and ate go together. Ite and us go together. So if it ends in ate, you change it to ick. If it ends in ite, you change it to us. Name this. Oh, question.
So we don't put hydro?
You do not put hydro. No. Hydro is for the binary acids, no oxygen. If there's oxygen, you don't use hydro. And that's hard to remember. But hydrochloric acid and chloric acid are different. So we have to be careful. The rules of nomenclature can seem a bit confusing. But they were actually worked on by many scientists over many years to make sure that we had a consistent way of naming things so that everything has one unique name. And so there's no, oh, well, you could name it this way or you could name it this way. No, there's one systematic name. Some things have common names too, but the systematic name is unique to that one specific compound. So let's look at HNO2. First of all, is it an acid? Yeah, it starts with H and it's dissolved in water. And then what kind of an acid is it? Is it an oxyacid? Does it have oxygen in it? Yeah, it does. So we're going to use the rules for oxyacids. So we need to identify what that ion's name is. Nitrite. Nitrate is NO3. This is the light version. So that's the nitrite ion. So we're going to change the ending to us. Ite and us go together. Nitrous, and then the word acid. So that's nitrous acid. Nitric acid is HNO3, and they're different. Any questions? This requires some practice, and we'll be practicing, I think we have a nomenclature worksheet coming up next week. So what about writing a formula? Write the formula for perchloric acid. Well, obviously it's an acid. It's got the name, it's got the word acid in its name. Does it start with hydro? No, it doesn't. So this must be an oxyacid. The binary acids, what I call the other acids, their names start with hydro, and then you've just got hydrogen and a nonmetal. But this does not. So now what we have to do is the reverse. We need to take this ick ending. Ick goes with 8, right? So this comes from or contains perchlorate ion. What's the formula for perchlorate ion? ClO4. And what's the charge on it? -1. When you put an acid in water, it ionizes and forms 2 ions. One of the ions is hydrogen, and the other will be this anion. So now we use our skills from naming ionic compounds to figure out how many hydrogens do we need to balance the charge on a perchlorate ion. Well, we just need 1. So the formula for this is HClO4. That's perchloric acid. So that example kind of got ahead of this slide, but when an acid, when a name ends in acid, the formula is going to start with H. So you write the formula like it's ionic, even though it's actually molecular, because when you put it in water, it forms ions. If we see a hydro prefix, it's a binary acid. If there's no prefix, it's an oxyacid. It's going to have oxygen in it. For those oxyacids, we'll do what I just did in that example. If the ending is "ic," the polyatomic ion ends in "ate." If it's "us," it ends in "ite." And so you write the ion formula. So here's some extra examples, because I didn't think there was enough in the book. So hydrocyanic acid. Let's start off with a weird one. Well, is this an oxyacid or a binary acid? It's a binary acid because of this prefix hydro. Where's my pointer? There it is, hydro. So this does not have oxygen in it. So now we're looking at cyanic. The other acids, we did things like changing fluorine to fluoride. We had an element. But is there a cyanic element? Cyanide is the closest thing we can think of, right? Cyanide. This is a polyatomic ion, but it's not an oxyanion. So cyanide. This cyanic comes from cyanide. So we're going to use the charge on this ion and hydrogen to figure out how they go together. And it's going to be 1-to-1, HCN. Oh, and what I forgot on the previous slide is we really should write aqueous, because some of these things also exist as pure molecular compounds. So that's hydrocyanic acid. And he is the reason, I don't know why it's a he. He is the reason that I don't like the name binary acid, because that's not a binary acid, but it's named like a binary acid. So was that confusing? I didn't set out to confuse you this early in the morning. Phosphoric acid. Oxyacid or binary acid? Oxyacid, because it doesn't start with hydro. So we've got this ic ending. Ic comes from 8. Ric 8. Ic and 8. So this is from phosphate. We need the formula for phosphate. PO4, 3 minus, and then there will be hydrogens with that. So the formula for this one will be H3PO4, and then we really should put AQ. I'm not going to try to trick you on the AQ. I might accidentally. Questions? How about this last one, hypochlorous acid? It's an oxyacid. Hypo and hydro are real similar, especially at 7:30 in the morning, but they're different. Hypochlorous, this is an oxyacid, and so we have to change the us to ite. This forms hypochlorite ion, which has the formula ClO minus, and then we're combining that with hydrogen, so we get HClO aqueous. That's hypochlorous acid. It's a whole family of acids with hydrogen and chlorine in them. Acid rain. You've probably heard of this. Some pollutants, including these guys up here, will form acids when they mix with water. There's water in the atmosphere, right? So these pollutants come out of chimneys or vehicles. They combine with the water in the atmosphere and form an acid. Then when it rains, the acid comes down with the rain. So that can flow into lakes or streams and make the bodies of water more acidic. It can fall on trees and cause them to lose their leaves and die. And it can also erode statues. There's a picture of two statues. They originally were identical for the most part, and this one's been rained on a lot and that one not as much. And you can see that the acid in the rain is slowly eroding the statue away.